And hello again. And today we are going to talk about spontaneity. Let's be spontaneous and how the concept of entropy combines with the concept of enthalpy to lead to a definition of spontaneity when it comes to chemical reactions. So before we talk about spontaneity, though, let's go back and revisit this concept of entropy. Now, just like enthalpy is given the letter H um, for reasons that probably have something to do with German, I'm not really sure. Entropy is given the symbol capital S for entropy. I know it gets a little confusing, just deal with it. And as we mentioned before, entropy can be considered a measure of the disorder or spreading out in a system. So if you have particles in a system that spread out, or if you have a molecule that falls apart, you're making more disorder, and that's an increase in entropy. So systems are being driven. So remember those driving forces. We're being driven to an increasing state of entropy. We want to see this disorder increasing, the spreading out increasing. And so this is the natural tendency, is towards increasing disorder. This is part of the second law of thermodynamics. The second law of thermodynamics, the first law was conservation of energy, where the Q of the reaction had to equal Q of the, or negative Q of the water. And now we've got that the entropy of the universe, and this is the whole universe, the entropy of the universe is always increasing. And this is going to help us to understand how spontaneity works and what it means in the context of chemical equations. Now, we could measure absolute entropy. In fact, it's the only thermodynamic quantity that has an absolute zero to it. This diagram down to the right, you can see at 0 Kelvin for a perfect crystal, the entropy is set equal to 0. And this is the third law of thermodynamics. But we're not really going to concern ourselves with that very much. It's like the other laws, it's subject to a little bit of understanding that it doesn't really work exactly that way. So an entropy change is positive, and we call that a favorable entropy change, is positive for a tendency to proceed to higher entropy. So a positive entropy change is higher entropy, is higher disorder. But this tendency to proceed is not enough. It can help, it can make a reaction be more likely to be spontaneous, but by itself, it's not enough. And just like a change in entropy, in enthalpy, a decrease in enthalpy isn't always necessary. You can have a positive enthalpy change and still have the reaction go forward. And we're going to kind of see how that works today as well. So one of the things I'm going to ask you to do is to recognize, given a particular process, whether the change in entropy is positive or negative. Now, we're not going to put specific values on this. We're not going to do calculations of just a change of entropy like we did for the change in enthalpy. We will use values later on, but I'm going to give you those values. So a couple of years ago, one of our students came up with the idea that in order to understand increasing entropy, if we look at the fact that starting at solids, and this diagram on the right is going to help us. So let's go over the diagram on the right. So we have the solid here. We melt it. So as we come up the curve, increasing temperature at first, and increasing temperature is always going to lead to an increase in entropy. And then when you melt, you increase the entropy, you're spreading things away. So solid to a liquid, there's the liquid. Increasing temperature again in the liquid is going to increase entropy. Then when we boil to get to the gas, it's also an entropy. Look at that. It's a large increase in entropy. And then again, once you get to the gas, increasing up the gas is going to get us to an entropy as well. Now, what's not in this phase diagram is aqueous solutions. And I'm going to stick them in there because they're important in a lot of ways to us. So we have this acronym called Slag. Slag stands for solid to liquid to aqueous to gas. And as we go through those different phases, that's always an increase in entropy. So the delta S is always positive. The entropy is always increasing. Going from a liquid to a gas, as you saw there, that's skipping by the aqueous phase, that's increasing. Going from a solid to an aqueous or liquid to an aqueous, not a gas to an aqueous though, because gases always have the highest entropy. And as we'll see in a moment, going from an aqueous to a gas actually has an increase in entropy. And this is why the solubility decreases as temperature increases, because as the temperature increases, the change in entropy becomes greater and greater to make that gas, and so you're going to make that gas. Other than that, mixing things, so mixing up a solution in general is going to increase the entropy. Taking a gas and expanding it. So down here, I have an actual picture of something that is a spontaneous process. So if I start off with these two bulbs and notice that the valve in between them is closed. So if the valve is closed, we have all the gas on the left side. And when we open that valve, the spontaneous process is for the gas to expand. So the gas expands into both containers, expands into the whole volume. And you would be very surprised, at least I hope you'd be very surprised, if without doing something that we go back the other direction. So that other direction is not spontaneous. That means that under normal conditions, it's not going to happen. And that's basically what spontaneity is. And then we'll get to the definition of spontaneity in a few minutes. Another way that you can think about having an increase in the entropy, a positive delta S, is to have an increase in the number of moles of a gas during a reaction. And we'll see an example of this down below. And as I said above, gases have the highest entropy of all the states. And for that reason, we're going to focus in on the gases in a reaction when we look at changes of entropy. To get a process that's not favorable, that has a negative change of entropy, go the other way. So gas is becoming aqueous. The opposite process is a gas becoming a liquid. So condensation, a liquid becoming a solid. Crystallization, so forming a solid, crystallizing, forming a solid out of a solution. These are all going to be processes that have a negative entropy change. And in order to get these to happen, something else is going to have to happen along with it. So I want you to follow along. And if you want to pause the video before we reveal the answer for each one of these, you can do so. I want you to predict what the sign of the delta S. All I want to know, is it positive or is it negative for the following processes? So forming raindrops forming from a vapor. So what do you think? Pause for a moment. And now what did you come up with? So what's going on here? We're taking a gas and we're making a liquid. So we just saw up above that a gas going to a liquid has a negative delta S. It's a decrease in the entropy. This is a tricky one. Air being pumped into a tire. What are you doing with that gas? Think about it. All right. So as we think about it, what we're doing to the gas is being compressed. It's close, the particles are closer together, which means that it's not as spread out. And so that's also a negative change in entropy. How about gasoline vaporizing in a car engine? Pause and see if you can figure it out. And now let's start up again. Gasoline, if you don't know, gasoline starts off as a liquid. Maybe you've seen it pumped into your car as you stop at a gas station. Vaporizing means a liquid going to a gas. And so liquid going to a gas, there's that gas with the highest entropy. So this has a delta S. That's a positive value. And finally, sugar dissolving in coffee. So what do we think here? Sugar is a solid. When we dissolve it, we make it into an aqueous solution. Coffee is an aqueous solution. And so this has a positive delta S as well. In reactions, you have to look at the number of moles of gas on both sides of the reaction. If we have an increase in the number of moles of gas, then we have a positive delta S, as it says over here. If we have a decrease in the number of moles of gas, we have a negative delta S, as it says over here. And if we have the same number of moles of gas on both sides of the equation, so reactants and products, it's okay to say, I don't know, I can't tell. And you would need more information that you're not going to be privy to, so you're not going to have to worry about it. So always count up the number of moles of gas on both sides of the reaction. In E, we have in the reactants, we have only a solid. Solid doesn't count. We have 0 moles of gas. In the reactants, we have solid, and we have 3 moles of gas. So the number of moles of gas went up. We're making more gas. More gas means a positive change in delta S. In this next one, in F, we start off, those are both gases, so we start off with 2 moles of gas. We end up with 1 mole of gas. The coefficients are important here. And so we went from 2 to 1. The number of moles of gas decreased, and so we have a delta S that's negative. And finally, in E, how did that become E? That should have been a G, right? So in G, we start off with 2 moles of gas. We end up with, there's that coefficient, that's important. We end up with 2 moles of gas, 2 going to 2. And so your answer is, I can't tell. I think that's a better way of saying it than don't know, but that's okay. Don't know kind of says, I'm not sure what I'm doing. Can't tell means I know that because it's the number of moles of gas are the same on both sides, I'm not going to be able to tell the difference. So a lot of your homework is going to deal with looking at different processes and determining what the sign of the entropy change for those processes is. Now, let's move on to the concept of entropy. So, the concept of spontaneity. Spontaneity, and the test we're going to put on it asks the question, does a reaction or a process, the process, it can be a physical process like melting or freezing as well, occur under the given conditions? And the given conditions are going to involve temperature. It does not indicate, however, the speed or the rate of the reaction. That's something called kinetics. And we're going to start to cover kinetics next week as the second part of this unit. That's how fast reactions occur. For example, a reaction like burning wood. Burning wood is very spontaneous. We'll see why in a moment. So why doesn't your wooden desk or your wooden house just burst into fire? Well, it's because of kinetics that prevent it from going too fast. And we'll see how that works next week. So to get the concept of spontaneity, we have to look at a combination of delta H, the enthalpy change, and delta S, together. And when we put them together, not individually, when we put them together, we get this concept of Gibbs free energy. And if you're like me and you like NCIS, you're thinking of Leroy Jethro Gibbs. Nothing to do with him. And finally, we have a symbol that matches with its name. Gibbs free energy is delta G. So delta G is going to tell us how spontaneous a process is. So enthalpy change, entropy change by themselves can't tell us, but the Gibbs free energy change can. So let's take a look at what Gibbs free energy means. Gibbs free energy is the amount of energy, and we're not talking about just heat now. We're talking about things like gases expanding give us work, and that's energy. The amount of energy released by a process to do work. As you saw in the driving forces video, things like moving that car, those old-fashioned race cars, those were pretty funny, weren't they? Moving a car forward, something doing to do work. Now, when that happens, when you have that happen, the entropy of the universe increases. Now, the entropy of the universe is going to increase. And one of the ways the entropy of the universe can increase is that the entropy of the universe increases. So anytime you increase the entropy of the universe, you're increasing of the surroundings. Increasing the entropy of the surroundings will help to increase the entropy of the universe. And that's why an exothermic process is favorable. So not only is this downhill, so let's talk about this for a moment. It's favorable delta H. This is downhill, and it's more favorable. But the other thing is this, the delta T, or actually let's call it the T of the surroundings, goes up. And as we saw, having the T of the surroundings goes up means that the entropy of the surroundings also goes up. And so having that be a positive thing, a positive change in the entropy of the surroundings, is more likely to give us a positive change in the entropy of the universe. So a positive delta S of the universe is more likely. But it's no guarantee. It's favorable, but there's no guarantee, because we still have the entropy of the system to worry about. And if we have a negative change in the entropy of the system, it might counterbalance the positive change in the entropy of the surroundings, and it might end up being a negative change in the entropy of the universe, which would not be a spontaneous process. However, notice that if we have a positive change, an increasing entropy of the system, these are both of the system, that's also a favorable process. Again, it's not guaranteed, because you might have a positive change in the entropy of the system, but a negative change in the entropy of the universe. A negative change in the entropy of the surroundings would be a temperature going down. So temperature decreasing means that the delta S of the surroundings is negative, and that's why an endothermic process is not favorable. But here's the thing. Notice we've got two favorables. We've got a delta H that's negative being favorable. We've got a delta S that's positive being favorable. And so what we do is we take the two of these things and we put them together in an equation. And this equation is on your chart B. And this equation tells us that if we take the entropy change in the system, enthalpy change, the delta H of the system, and we subtract the Kelvin temperature, it has to be Kelvin, otherwise this doesn't work, times the delta S, the entropy change of the system, this is going to tell us whether or not it's spontaneous. And in order to be spontaneous, delta G has to be negative, because a negative delta G guarantees a spontaneous process. It guarantees that the delta S of the universe is positive. All right, so negative delta G of the system, positive delta S of the universe, and that guarantees a spontaneous process. So if you look at this equation, you can see a couple of things. If the delta H is negative, less than 0, and the delta S is positive, they are both favorable. And because they are both favorable, they both lead to increases in the entropy of the universe. So a negative delta G is, if it's negative, is always negative, no matter what the temperature. So it's always negative, no matter what the temperature. Again, it's going to depend on temperature. Then this is a spontaneous process. And we can say it's spontaneous in the forward direction. Now, here's the opposite. If we have a delta H that's positive, so that's not spontaneous, and a delta S that's negative, they both lead to a decrease in the entropy of the universe. Not good. So those are both unfavorable. It doesn't matter what temperature it is, the delta G is always going to be positive, and so this is always not spontaneous at any temperature. Now, here's the tricky ones. If we have a system in which they both have the same sign, either both positive, both negative, what's going on is they're playing off each other. So both positive, both negative, one is going to be favorable and one is going to be unfavorable. When that happens, the delta G depends on the temperature, and you'll have to do the calculation to determine whether or not delta G is positive or negative. So let me give you a couple of examples. Boiling. You know that to boil something, it's spontaneous at high temperatures. If you don't get the temperature up high enough, it's not going to be spontaneous. It's not going to happen. Well, what do we know about boiling? Boiling is an endothermic process. You have to put energy in. So the delta H is positive. That's unfavorable. How do we overcome that? At high temperatures, boiling is also a positive delta S. We go from a liquid to a gas. So this is endothermic. Liquid to a gas, that's a big favorable. At high temperatures, that favorability takes over, and that's why things boil at high temperatures. Meanwhile, freezing. You should know at this point that freezing takes place, it's spontaneous. And remember, spontaneity, as we said, depends on the conditions. So it's spontaneous at low temperatures. How does freezing work? Well, freezing, the delta H is negative. It's an exothermic process. It releases energy. You have to pull energy out of water to get it to freeze. But when you freeze, you have a negative delta S. The delta S, you're going from a liquid to a solid, and that's a negative delta S. So when you get low enough in temperature, the exothermic part of the process is more important, and that's why that works. All right, so you really only have to know that you're going to look at the change, you're going to look at the signs, and you're going to say, okay, if they're both positive, they're both negative, I have to do the calculation. If one is positive, one is negative, then unless I ask you to do the calculation, you can say, oh, okay, if they're both favorable, then it's going to be spontaneous at all temperatures. By the way, spontaneous at all temperatures if we have a negative delta H and a positive delta S. And If it's negative and if it's negative delta S and positive delta H, then it won't be spontaneous. So let's take a look at how we do these calculations, and then we'll be done with the lesson for the day. So here's a reaction. We've got sodium chlorate, and there's that little delta, so we know that we're going to have to heat it up. That delta telling us, I thought I picked the blue pen, telling us that we have, how did that happen? Scrolled all the way up. Have to put heat in. So that tells you that this might be a reaction that's dependent on having a high temperature. Now notice that the delta H is positive, the delta S is also positive. So just like boiling, this fits. This is going to need to be a higher temperature in order to be spontaneous. But I want to know, is it spontaneous at 25 degrees C? All right, so we've given you the delta H and the delta S. Don't ask where those numbers come from. You will never be responsible for them. I will always give you those numbers. Now, here's the thing. When we calculate delta G, the thing we have to do is we have to, and I'm going to have this in the homework, we need to calculate the delta G. And I want the units to be in kilojoules per mole, because delta G's are usually measured in kilojoules per mole. Now, the delta H is given to us in kilojoules, but the delta S is always given to us in joules. And the units are joules per mole times Kelvin. That Kelvin is there so that when we multiply it by the temperature in the equation, those temperatures cancel out. So what we're going to have to do is do a little convert alert. So we have our 176.8 joules per mole Kelvin, and we're going to multiply by 1 kilojoule over 1,000 joules. And that's going to get us 0.1768 kilojoules per mole times Kelvin. Again, remember what I told you about, if you're not quite sure, we went from 176.8, the joules. I don't have to put the rest of the units in there because joules is the only thing we're worried about. To get to kilojoules, the same as going from 1,000 joules is the same as 1 kilojoule. So you know you have to divide by 1,000 to get to where you're going. So dividing by 1,000 is going to get us the delta S. Now we can put that into our equation. Oh, not quite yet. We have another convert alert. So 2 convert alerts here. Don't forget to do these conversions, please. The other convert alert, 25 degrees C. I told you we had to be in Kelvin. We need to have no negative numbers here. Otherwise, it's going to mess up that equation. So we're going to add 273 to 25 degrees C, and we're going to get 298 Kelvin. Now we can plug all those numbers into the delta G equation. So let's bring our delta H up down from above, positive. I'm going to put the positive sign in there just so that you know it's there. 19.1 kilojoules per mole. Now I'm going to subtract off the temperature is 298 Kelvin, and we're going to multiply that by 0.1768 kilojoules per mole times Kelvin. Notice the Kelvins cancel out, leaving us with kilojoules per mole and kilojoules per mole, which is great because we have to be able to add 2 numbers with the same units. When we do that, we do this full work, we get a total of negative 33.6 kilojoules per mole. And because of that, it is spontaneous. And the way we know it's spontaneous is because the delta G is negative. All right. So I hope that you understand what's going on. The homework, and this homework is going to be due Monday morning at 7:30, along with your lab. Don't forget about the lab. Go and do that homework and have a wonderful weekend.